Hello students, let's have some discussion on exercise set number 3. In the previous exercise set, the exercise set number 2, there wasn't much to discuss because all the problems there were straightforward. I'm not saying they were easy, they were actually difficult, but the problems themselves were straightforward. With a statement and then prove it, and the proof was through algebraic manipulation. That was it. Here in exercise set 3, there are some problems that require some clarification, and let's talk about those kind of problems. We have these 3 problems in 2.1, and then the others are coming from 2.2. Let's go to 2.1. First, the table of contents, and 2.1. Okay, all right, that's the page I have to go. Okay, here we go. And first we have some matrices A and B with these numbers. We can calculate A plus B, 3B, negative 2B, A plus 2B, and so on. They are straightforward really, just computations. And similar problems recur. And finally at number 5 we have something worthy. Let A and B be arbitrary n by n matrices. Show that the transpose of sum is sum of the transpose matrices. Let's go to my notebook and talk about it. Oh, by the way, in my notebook, I'm using transpose notation like this. Instead of T on the upper left-hand side corner, which is rather difficult to typeset, I'm using top right-hand side corner. And this is widely accepted notation as well, so I offer no apology, even if sometimes it may cause a bit of a confusion with the power. I'm not going to use T as a power. If you see a power, it's going to be K or N or things like that. All right, let's talk about this. So what do you have to know here? And first, you got to know what is a transpose. So if C is Cij in matrix expression, M by n matrix, then what is a transpose? Transpose is nothing more than C of Ji. We simply switch I and J. This is ith row, jth column, and this is jth row, ith column. So column goes to row, row goes to column. That's about it. And then consequently, the size of the matrix becomes n by n. And this is what the transpose does. So you apply that to this matrix A plus B, and then do some index computation. In the end, you should be able to get that. So this is what transpose is. And then what you have to prove, what is A plus B in matrix. In component expression, it's A of Ij plus B of Ij, isn't it? Because we are adding up each component. So in general, Ij component of A is added to Ij component of B. And then the size of the matrix is, of course, M by N, like this. And then we have to take the transpose, right? So this should be transpose. And consequently, this should be transposed. And in matrix components expression, what is this? Well, that's something you have to figure out. And then, okay, let me give you this hint. Row is becoming column, column is becoming row, so we have to have n by n instead of m by n. And what comes over here, and then how to calculate, and then eventually whether you're going to get that, that's something you have to get. And if you look at the size, yes, that's true. This is transpose, so this is n by m matrix. So yes, m by n matrix is here. So as far as size is concerned, it's okay. As far as the components are concerned, I'm going to leave those to you. And another problem here, this time scalar multiplication. Similar type of problem, if not exactly the same. Let's go to the PDF file again, and then let's see. I assigned 5, 6, and 10. And what are the other problems here? 6 and 7 about diagonal elements and A and A transpose. 8 and 9, pretty much elementary. Let's go to number 10. Is this really worthy? It's a proof problem, yes, so it looks like it's a worthy problem as well. Okay, let's go to my notebook again and then open up. And this is what we have to do. If A is a square matrix, then A plus A transpose is a square matrix as well. Excuse me, it's of course square matrix. It's a symmetric matrix. What do you mean by symmetric matrix? What is symmetric matrix? Matrix C is it has to be a square matrix. If it is not a square matrix, then it cannot possibly have a symmetry. A square matrix C is called a symmetric matrix if transpose is itself. Okay, that kind of thing is called symmetric matrix. And can we think of some example like this? Let's see. Okay, about 4 by 4. Okay, all right. Is it too big? I don't know. Let's just name this matrix as C, and then let's see. Anything can be here, and then here, if I say 2, then this is first row, second column. So second row, first column, these two have to be the same. So that transpose doesn't change anything. If this is, say, -5, this also has to be -5. So that if I take transpose, we get the same thing. If this is 0 and that's 0, I have too many integers here. This can be anything because if I transpose, it stays itself. Let's see, this time let's take square root of 2, and this has to be square root of 2 as well. And then this is, say, 3/2. That also has to be 3/2, kind of like that. And then finally this one. Okay, all right. This kind of thing is a symmetric matrix. Okay. And then what do you have to prove? This is a symmetric matrix. So this is just an example. We must prove that transpose of this has to be itself. So transpose of this has to be itself. So you can consider this is a C, and this is C transpose, and that's equal to C again. So how do you prove this? Well, you can use a component expression, and this you can use Aij, and this one, what do you have to use for A transpose? And then take the transpose again, and so on. Okay, all right. You've got to remember what the transpose is. Okay, all right, so much for this problem. How about the next problem? A square matrix A is called skew symmetric if A transpose is negative of A. Can you think of an example here? Let's see. This is as good as any, so let me copy and paste this. Okay, this is an example of a symmetric matrix. If I take transpose, so here, if I define like this, then transpose is equal to C. If I take transpose, row becomes column, column becomes row. So this one, for example, first row, third column goes to third column, first row, and have to be the same because we have to become the same matrix again. So we have symmetry with respect to the diagonal. But this time now we have skew symmetry, so we need negative sign. So how do we have to change this? Well, this has to be negative so that one is positive, the other has to be negative. And if this is positive, the other has to be negative, kind of like that. 0 and then negative 0, that's okay. And one of them has to be negative so that, you see, negative of this is that and vice versa. Change this into negative and then change this to positive. And are we all done? No, not yet. Check the transpose, then it'll stay itself because we have first column, first row, so even if you change column and row, it stays the same. But negative of itself, if they transpose, it becomes negative 1, but negative 1 is not equal to itself. So the only number who is the same as negative of itself is 0. So we have to have 0 in diagonal. As a matter of fact, that's something you have to elaborate in part C. What can you say about the diagonal elements? As you have seen, they have to be 0, but why? Well, you have to explain it, or better, you have to prove it in 1 or 2 sentences. Good luck about that. And let's go back to part B. This is an example of skew symmetric matrix. Show that any square matrix A, the matrix A minus A transpose is skew symmetric. Here A plus A transpose is symmetric. A minus A transpose is skew symmetric. We have some kind of duality going on here. We have negative, so we have negative. What do you have to prove? So transpose of this is negative of itself, right? Transpose of this is negative of itself. This is what you have to prove. A little bit of word of caution here. We have the first sentence, which is written in terms of character A, and second sentence also with respect to character A, but these are two different characters, you see. It would have been a little bit easier to understand if the textbook author used two different characters like this. A matrix C is called skew symmetric if transpose is negative of itself like this, so that you can clearly see that first sentence and second sentence are talking about two different matrices. In that case, no confusion there. And this one is C, and C transpose is the left-hand side, and this one is C, so we have minus T as the right-hand side. So yeah, we are looking at this kind of expression, and this is what you can prove. Can you prove it using all those components expression, ij expression? Well, good luck. This is, of course, small aij, and what is this general component here? And then what happens if you take transpose? Good luck. One teeny weeny little comment here. Let's go back to that textbook expression here. Yes, our textbook author define a matrix A to be skew symmetric if A transpose is negative A. Our textbook author is using the same character A. And show that for any square matrix A, the matrix A minus transpose of A is skew symmetric. Here you have to be careful, and you have to note that this A in the first sentence and this A in the second sentence are two different A's. They are unrelated. If they had been if our textbook author used 2 different characters like I did, the problem would have been a little bit easier to understand. Our textbook author did not do that, and probably he must have thought that at this level, at 3000 level, students should be able to see that the first sentence and second sentence are unrelated at this level. Well, it would have been nice that everybody see it that way, but just in case not everybody sees it, I rewrote the problem, called it a clarification. Okay, so much for 2.1, and let's talk about 2.2 in a separate video. Thanks.